video. So AC க்கு மாத்திர வேண்டியது நெட்ல நிக்க கூடாது. இந்த ரேஷியோ மோட் உண்டா ஒரிஜினல் ரேஷியோ உண்டா 140 தாண்டப்படுது சார் அதான் இந்த டைம்ல இன்றைக்கு மோனியம் அப்படில நூற்றி 161 வந்துட்டு பரவாயில்ல ஸ்டார்ட் பண்ணுவோம். Okay, so we will start. Last time we talked about upper limit and lower limit of a sequence, right? So we see that the sequence, if it is bounded, it not necessarily will have a limit, but anyways, in that case, we can define upper limit, that is lim sup, and lower limit of a sequence, right? So and then we see how we can define that by using the supremum and infimum of the subsets which we generate from the set of elements in the sequence, right? So today what we are going to do is we are going to start proving some important results associated with the limit of the upper limit and the lower limit of the sequences, right? So I will start with the limit associated with the upper limit property. So I will write this as a theorem, right? So you obviously know we should have a bounded sequence first to make sure that the sequence has a limit, right? So xn is a bounded sequence, right? And then we name, right, L be the upper limit, right? And so let us name L as the upper limit of the sequence, right? This is true if and only if, right? So I can say then L is the upper limit of the sequence if and only if for every epsilon positive, right, there exists a natural number such that, right, xn is less than L plus epsilon, right, for all n greater than n, and the other inequality L minus is for infinitely many. Right, so this is the results which we are going to prove associated with the upper limit, right? So definition of upper limit. So what we have is, if L is the upper limit of the sequence, then for any epsilon positive after a certain natural number n, right, all the index beyond that natural number, xn is less than L plus epsilon, right? At the same time, for infinitely many n, xn will be larger than epsilon, right? So xn will be larger than L minus epsilon. So we want to prove this, right? So if you want to prove this, right, so you know you have to prove two things. One is, if L is the upper limit, right, then this one is true. Right, so if this is the upper limit, then we have to show this one is true. And if this one is true, then we have to show this one is the upper limit. Right, so that is what we wanted to show. Okay, so we will start assuming that L is the upper limit. Right? So okay, so let's say L is the upper limit, right? So I'm starting with this. Right, so xn upper limit is equal to L. Then what I want to show is, I want to show that L minus epsilon is less than xn for infinitely many n, and L plus epsilon is greater than xn for all n after certain point. Right? So because this is the limit, right? So you know that, right? So this is true, right? Where mk is the supremum, right, of the sets xn such that n greater or equal to k. Right? So this is the definition we studied last time, right? So if L is the limit supremum, right? So if L is the upper limit, then for every epsilon positive, so you know I can assume epsilon greater than 0, that's fine. Right? The distance between mk and L is less than epsilon, for all k greater than n, where mk is the supremum of the subset of the sequences, right? So clearly you know that, right? From this you know that L minus epsilon is less than capital M, right? N plus 1. Right, so that is the consequence of this, right? For all k greater than n, mk minus L is less than epsilon. So for all k greater than n, L minus epsilon is between mk and L plus epsilon. Mk is in between L minus epsilon and L plus epsilon, right? So in this case, we can say that it is true for n plus 1. So we write n plus 1, right? Okay. But you know that we define mk as the supremum of the set xn with n greater or equal to k. So mn plus 1 is the supremum of the set xn with n greater or equal to n plus 1, right? So clearly, right? So I can put equal also. So clearly, the supremum is the upper bound, which you all know from chapter 1. So mn is greater than xn for all n greater than n. So if I combine both of them, I get one inequality, right? So if I combine both of them, then xn is strictly strictly less than mn plus 1, but that is less than L plus 1. So xn is less than L plus epsilon for all n greater than n. And because if it is greater or equal to n plus 1, then it will be greater than n. Right? So this is clear. One side of the inequality we prove, right? So xn plus 1, mn plus 1 is greater than xn for all n greater than n plus 1. Therefore, by combining this and this, we get one part of the proof. Now we have to go to the other part, right? So we have to show that the other side is true. And so let's do that. Now you take this side of the inequality. Right? So let me start with that. L minus epsilon is less than m n plus 1. Right? So this inequality is there. So I start with that. Right. If I have that, right, then obviously you know okay. So this is again something we studied from chapter 1, right? Because you know mn plus 1 is the supremum of this set, right? But you have L minus epsilon less than the supremum. So clearly it cannot be an upper bound, right? So L minus epsilon cannot be an upper bound for this set, right? So if this cannot be an upper bound, then this is again something we studied in chapter 1, right? If the value, if something is not an upper bound of the set, then we say that we can pick one element at least inside the set which is larger than that term, right? That real number. Because L minus epsilon is not an upper bound, you can pick one element inside the set, xn naught, which is the name I gave here, right? Such that this is greater than L minus epsilon, right? But you can continue doing this. So now what I am going to do is to okay. So now what I am going to do is to I am going to say okay. So what I am going to do is to now I am going to get a set, right? So obviously I pick n naught which is greater than n plus 1, right? So I take set of all xn such that n greater than n naught. So I am taking a smaller set, right? So you notice that this is a bigger set. I take less element from that, right? So in that case, obviously, again, the supremum is greater than L minus epsilon. Right? So same argument. So L minus epsilon cannot be the upper bound of this set, right? Right. So you notice that because you pick xn as a subset, right? So xn such that n greater than n naught as a subset of this L minus epsilon supremum of that is larger than L minus epsilon. So same argument like this, right? L minus epsilon cannot be an upper bound, right? So if that cannot be an upper bound, then you know you follow the same argument. So this time you pick a different index. Right? So then you can pick some n1, right? New index n1 such that xn greater than, right? So xn1 greater than L minus epsilon. So if you continue doing this, you will ended up picking infinitely many xn's such that, right, this inequality holds. Right, so if you continue doing this, you can see that you can continuously picking up xn1, xn2, xn3, xn4, xn5, and so on, right? So that means eventually you will pick infinitely many numbers, right? So for all those numbers or for all those terms of sequences, L minus epsilon is less than that xni. Right? So that means you can even pick infinitely many n such that xn is greater than L minus epsilon. So we prove one part, right? So if L is the lim sup, then we show that xn is less than L plus epsilon for all n greater than some capital N, and then we prove that xn is greater than L minus epsilon for infinitely many n. So now what we are going to do is we have to show the other way around. If these two inequalities are true, then we have to show that the sequence has an upper limit, and that upper limit is n. Right? So we have to show. So we will start proving that. The converse part. Okay, so prove the converse. Right, so conversely, let us suppose that the sequence has a value L such that their x(n) belongs to natural number such that, right, xn less than L plus epsilon and xn is greater than L minus epsilon for infinitely many n. Right, so let us assume these two are true, and using this we have to show that L is the upper limit of the sequence, right? So if we want to do that, let us define this, right? Okay, so let us define this. AK be the set of elements in the sequence such that the index is greater or equal to k. Okay, so for the sake of the results, let us say that this one is epsilon over 2 and epsilon over 2, right? So just to make sure that you get epsilon at the end, we will rename this as epsilon over 2 and epsilon over 2 so that we can. So actually I have to write the same line again with epsilon over 2 and epsilon over 2 just to save the time and save the space. I change there as epsilon over 2, right? So that's not a big deal, right? And so then right, because for all n greater than n, xn is less than L plus epsilon over 2, supremum of an plus 1 will obviously be less than L plus epsilon over 2, right? Right, so that is clear, lesser equal, I can say. So because all the elements in the set after certain n is less than L plus epsilon over 2, the supremum of the set is obviously less or equal to L plus epsilon over 2. So that is basically less than L plus epsilon. So now you know why I changed this to L plus epsilon over 2, right? Because I have to have strict inequality so that I put epsilon over 2 so that I can eventually write this is strictly less than L plus epsilon over 2. Okay, right. But this is something we studied already. Right, so the sequence of supremums is a decreasing sequence. Last class also we see that, right? So the sequence of supremums is a decreasing sequence, right? So because you are reducing the size of the set, so obviously the supremum is reducing. So it is a decreasing sequence. Because supremum is a decreasing sequence, if the supremum of a larger set, right? So in set with the larger index is less than L plus epsilon, then for all n, it will be less than L plus epsilon. Okay, so because supremum is a decreasing sequence, right? But for capital N plus 1, it is less than epsilon plus L plus epsilon. So because it is decreasing for all n, the supremum of the set an will be less than L plus epsilon. So we have one side of the inequality here, right? Now we take the other hypothesis, right? The xn is greater than L minus epsilon for infinitely many n, right? So this hypothesis we take and we get one side of the inequality. Capital Mn is less than L plus epsilon, right? So now we take the other hypothesis, xn is greater than L minus epsilon over 2 for infinitely many n. So we can use that, right? So okay, so now here is what we are doing. Because xn is greater than L minus epsilon for infinitely many n, right? So there are many numbers, maybe 2, 5, 10, 15, 20, 100 and numbers go like that. But among those numbers, basically all are natural numbers. So you should be able to get a minimum number, right? A least number. Because if it is a set of natural numbers, you obviously know you can find a minimum number or least number. So for that least number, L minus epsilon is greater than, sorry, L minus epsilon is less than xn naught. So if that is true, then for this set, right? So for this set, an naught, which is a set of all xn such that n greater than or equal to n naught. So you remember, you take n naught as the least possible number which you pick from the infinitely many n's. So in that case, the supremum of that set is obviously greater than that, because all the elements in this set are greater than L naught, L minus epsilon. So supremum is obviously greater than that. Right? So now because you choose n naught as the least possible number among those infinite numbers, right? For some k greater than n naught, right? For some k greater than n naught, you know that xn will be greater than L minus epsilon, right? So because you know that n is the least possible number you pick in the sequence, right? So then in this case, supremum of ak is greater than L minus epsilon for all n, sorry, for all k greater than n. Okay? So same argument. As same argument like this, because xn is greater than L minus epsilon for all n greater than k, where you choose k as the number greater than n naught, supremum of this is greater than L minus epsilon. So you have supremum of two different sets, n naught and for some other k greater than n naught as well. Right? So because you have those numbers, so you know you have to combine both of them, right? But there is another number n1 here, n plus 1 n here, and then there is an n naught here. So you have to combine all of them, right? Because you know, if you want to show limit, you have to have a unique net n, right? A milepost which should be common for all. So here first you have a capital N, right? right? So you have a capital N and then you have a capital N node. So you have to take the maximum among those to make sure both the inequalities work for all the cases. Okay, so we choose N1 as the maximum of N node and N, right? So that is the maximum. So in this case, you see that in this case, if you take the supremum of AK, right, for all K greater than N1, right, for all K greater than N1, if K is greater than N1, then it will be greater than N, right? If K is greater than N, then supremum of this is less than N plus epsilon, right? So this says this is less than N plus epsilon. And again, if K is greater than N1, then K is greater than N naught. If K is greater than N naught, then supremum of AK is greater than L minus epsilon. So you have L minus epsilon as well. So this is what we wanted to show for the limit, right? So this is what we have. Right, so if you simplify this, if you write this in a common notation, what you have is for every epsilon positive, there exists a natural number n1 such that, right, supremum of AK minus L is less than epsilon for all K greater than n1. So clearly, this is the definition for the upper limit, right? So we see that definition in the last class also. So this says L is the upper limit of the sequence. Okay. So then L is the upper limit. Okay, so now what we are going to do is we are going to talk about the relationship between the limit, upper limit and the lower limit now. Right? So you notice that we have a limit, that is something we define first, and then we talk about upper limit in today's class and in the last class, and also we talk about lower limit as well, right? So last class again we talk about lower limit as well, and then we see that those limits are different, right? So upper limit and lower limit are not necessarily equal, but at some cases you know that they are equal as well. So here what we are going to see is, we are going to see what will happen when the upper limit and the lower limit are equal. Right? So interestingly, whenever the upper limit and the lower limit are equal, then that is what we call the limit of the sequence, right? So the upper limit and the lower limit, whenever they are equal, they are actually equal to the limit of the sequence, right? So if they are actually equal to the limit of the sequence, then we can say the sequence converges. So now we are going to develop a new criteria for convergence in terms of upper limit and lower limit, right? We are going to say the sequence converges if and only if the upper limit and the lower limit are equal to each other. So that is what we are going to do now. Again, theorem. Okay, so we are going to show that if the upper limit and the lower limit of the sequence are equal to each other, then we say that the sequence is convergent. That means limit exists. Right? So that is what we are going to prove. Right? So if it is convergent, then upper limit and lower limit are same. And if it's upper limit and lower limit are same, then it will be converging. Right? So proof. Right? So suppose Xn is convergent. So we say that the limit of the sequence is L. Right? So the standard notation, if it is converging, then it has a limit. So let's say it is L. So then you know for every epsilon positive, there exists a natural number such that Xn minus L is less than epsilon for all n greater than n. Right? So you know that. That is the definition for limit. We study. Right. So then we are going to show that the upper limit and the lower limit are same here. Right. So let's build up according to that. Right. So okay, so these are the notations we already used, right? So just I am reminding them, right? Because Xn is less than or equal to L minus epsilon and L plus epsilon, right? So Xn lies in between L minus epsilon and L plus epsilon for all n greater than n, right? Then for any k greater than that capital N, L minus epsilon will be less or equal to the infimum of that set. right? And then that is less than mk, but at the same time, you know, infimum is always less than or equal to supremum, but supremum is less than mn plus 1, but mn plus 1 is less than epsilon plus L plus epsilon. Right? So these are the combination of the results. So eventually what you have is this, right? So this is what you have. L minus epsilon is less or equal to mk less or equal to L plus epsilon. At the same time, L minus epsilon is less or equal to capital Mk less or equal to L plus epsilon. And so you have these two results. Right? So if you combine all of them, you know that L minus epsilon is less or equal to Mk less than or equal to L plus epsilon. Right? At the same time, L minus epsilon is less than capital Mk is less than L plus epsilon. And so you combine, if you combine both of them, then you get the definition of upper limit and lower limit, right? So okay, so from one of this, you get lim is this, right? So this, right? So from the first line, you get lower limit is L, and from the second line, second inequality, you get upper limit is L. Right? So if you combine all of them, you get limit is equal to equal. So upper limit and lower limit are equal. So that is not a big thing to do here. Right? So now what you have is the other case, right? Converse. Right? Right? So suppose you have these two, right? So then you have to show that there is a limit and that is L. Right? So because of 1, right? So there x is n1, right? Belongs to natural number such that xn is less than L plus epsilon or all n greater than n1. And from the other results, there x is n2 belongs to natural number such that L minus epsilon is less than xn or all n greater than n2. Right? So this is when you write the definition of lower limit is equal to L, you get this, right? And when you write upper limit is equal to L, you get this. From this, you can say for all n greater than n1, this is less than epsilon. For all n greater than n1, this is less than xn. You can always write from the definition, right? So I leave you to see how you get these two lines. Right? So now what you do is you combine them, right? So n is equal to maximum of n1 comma n2. So in that case, you know that there x is n belongs to natural number such that L minus epsilon is less than xn less than L plus epsilon or all n greater than n. Right? So that's, if you combine those two, you get for every epsilon positive, there x is n belongs to natural number such that L minus epsilon is less than xn less than L plus epsilon. So that gives you that the sequence converges to the limit L, right? So, right, so then this gives L minus epsilon is less than xn less than L plus epsilon. So the sequence converges to L. So that is what we want to show converges. So this is what you need to learn in chapter 2, the sequences, right? So in the next class, we are going to start talking about something called series, right? So that is a consequence of what you have in series. At the same time, we will try to put the tutorials on the LMS, right? So we are still preparing it. Once we finish preparing it, we will put it on the tutorial, and then we will conduct the tutorial classes at the last part of this course, right? So Saturday class, we will start chapter 3, right? So that is series. And I already posted the notes on LMS, sample notes, not the regular notes, sample notes. So we'll stop here and then continue on Saturday.